NASA's Artemis program is bleeding billions while facing massive delays. But aerospace expert Tim Dodd just exposed a superior alternative that SpaceX could implement right now. His Stubby Starship design eliminates 400 tons of dead weight, cuts refueling missions in half, and provides 700 meters per second more safety margin. The math is undeniable. This approach is faster, safer, and dramatically cheaper than NASA's current architecture. Yet NASA continues pouring taxpayer money into their flawed system. Why reject a proven better solution? Let's dive right in. To understand why these alternatives matter, we need to examine NASA's current plan, and the numbers are shocking. The Artemis mission architecture reads like a logistical nightmare. Before any crew launches, SpaceX must first send a storage depot to Earth orbit. Multiple tanker flights then carry fuel to this depot. The uncrewed Starship HLS launches separately, docks with the depot, refuels, and only then begins its 6-day journey to lunar orbit. That's 3 separate operations before astronauts even leave Earth, and each step introduces complexity, cost, and potential failure points. The situation becomes more troubling when you examine the hardware. NASA's Orion capsule weighs 26.5 tons, nearly 3 times heavier than SpaceX's Crew Dragon at 9.5 tons. Yet Dragon offers 50% more interior space for astronauts. As aerospace expert Robert Zubran puts it, NASA built an elephant when they needed a racehorse. The engineering constraints create additional problems. The SLS rocket cannot deliver Orion to low lunar orbit with enough fuel for a return trip. This limitation forced NASA to design the Lunar Gateway Station in high lunar orbit, essentially a $15 billion workaround that doubles the fuel requirements for any moon lander. Zubran's assessment is blunt. This Rube Goldberg solution will cost billions and delay Artemis for years. The financial reality supports his concern because each SLS launch costs approximately $4.1 billion compared to $400 million for a Falcon Heavy launch. This is where our story takes an interesting turn. Tim Dodd, known as the everyday astronaut, brings both aerospace expertise and independent analysis to complex space missions. His background allows him to examine NASA's plans without the political constraints that often influence official assessments. Dodd's investigation revealed a fundamental flaw in the current Starship HLS design. The spacecraft carries 20 to 25 tons of additional tankage in structural mass specifically for the translunar injection burn, which is what sends the spacecraft from Earth orbit toward the moon. Once this burn completes, all that hardware becomes dead weight, carried through every subsequent mission phase. The numbers barely close with little margin for error and boil-off when using a full-height HLS that does its own TLI, Dodd explains. In aerospace engineering, tight margins mean higher risk and limited operational flexibility. His solution elegantly addresses this core inefficiency. Create a shorter, stubby version of Starship HLS that never performs its own TLI burn. Dodd's Stubby HLS concept demonstrates how smart engineering can solve multiple problems simultaneously. The design works by launching the shortened HLS to low Earth orbit, where it docks with a separate translunar refuel depot. This depot, equipped with 2 Raptor vacuum engines, handles the TLI burn while both vehicles remain connected. The engineering benefits cascade through every mission aspect. The shorter vehicle has a lower center of gravity, dramatically improving landing stability on the lunar surface. The crew elevator system becomes simpler and more reliable. Ground operations require less complex equipment. Most importantly, the Stubby HLS needs only 400 tons of methane oxygen propellant for its round trip between lunar orbit and the surface. The current design carries hundreds of tons of unnecessary structural mass through these same maneuvers. The safety implications are significant. This approach provides nearly 700 meters per second of additional delta V margin, which is basically extra fuel for maneuvering. That's the difference between a comfortable mission and potential emergency scenarios. Dodd emphasizes a crucial point. Cargo and crew volume remain identical to the current design. SpaceX could implement this modification without violating existing contract parameters. Dodd doesn't ignore the engineering challenges his proposal creates. Performing a high-energy TLI burn while 2 massive spacecraft remain docked has never been attempted in spaceflight history. The docking mechanism must withstand multi-minute, high-thrust burns while maintaining perfect structural integrity and guidance control. The software systems must coordinate two separate vehicles through complex orbital maneuvers. However, the forces involved are surprisingly manageable. At full throttle, two Raptor vacuum engines pushing 1,870 tons of combined mass create only 0.3 g of acceleration. Even at burn completion, acceleration peaks at just 0.78 g, which is less than astronauts experience during routine launches. The Trans-Lunar Depot presents its own engineering requirements. With minimal dry mass and just two engines, it needs an expendable booster for initial orbital insertion. The depot's 19-minute burn time to consume 1,600 tons of propellant requires careful thermal management and propellant handling. Operational complexity does increase compared to the single-vehicle approach. Teams must coordinate two spacecraft through launch, refueling, docking, and TLI phases. Each additional step creates potential failure points that mission planners must address. Despite these challenges, Dodd's analysis concludes, the Stubby HLS concept is almost the only real viable option that has much greater margins and requires far less refueling once it's at the moon. While Dodd's proposal optimizes the current Artemis architecture, Robert Zubran suggests a more radical approach: abandon the Orion SLS system entirely. Zubran's credentials add weight to this proposal. As founder of the Mars Society and president of Pioneer Astronautics, he spent decades analyzing space mission architectures. His assessment of NASA's current approach is unforgiving. Dragon isn't just cheaper than Orion, it's better, Zubran states. The comparison supports his claim. Crew Dragon weighs 20% more than the original Apollo capsule, while offering 50% more internal volume. It's currently flying astronauts to orbit, while Orion remains in development. Zubran's mission profile eliminates multiple complexity layers. Falcon Heavy launches Crew Dragon directly to low lunar orbit with a fully fueled return stage. No lunar gateway station is required. No multi-billion-dollar SLS development continues. The mission requires two Falcon Heavy launches, one for crew transport, one for the lunar lander. Combined cost approximately $800 million. Compare this to two SLS launches at over $8 billion. This approach could begin within years using existing, flight-proven hardware. The technical risk is lower because every major component has already demonstrated operational capability. Understanding why NASA hasn't adopted these alternatives requires examining the intersection of engineering and politics in government programs. The Space Launch System represents manufacturing jobs across multiple congressional districts. Orion development employs thousands of engineers and technicians at traditional aerospace contractors. The Lunar Gateway project justifies international partnerships and creates additional funding streams. Adopting the superior alternatives would require acknowledging that years of development and billions in spending produce suboptimal results. It would eliminate established jobs and cancel lucrative long-term contracts. More significantly, it would shift control of America's lunar ambitions from traditional aerospace contractors to SpaceX, a company that's already disrupted launch services, satellite deployment, and crew transport. NASA Administrator Bill Nelson recently celebrated hardware milestones for Artemis II. The Orion stage adapter arrived at Kennedy Space Center from Marshall Space Flight Center. The full vehicle stack should be assembled by mid-October 2024. Each milestone celebration for existing Artemis hardware makes the engineering alternatives more compelling by comparison. The cost analysis reveals why these alternatives generate such strong reactions from both supporters and critics. Current Artemis mission costs include multiple SLS launches at $4.1 billion each, 15 or more tanker flights to refuel the HLS, lunar gateway operations and maintenance, and Orion operations with its 26.5-ton mass penalty affecting every mission phase. The Stubby Starship alternative would use standard Falcon Heavy launches at $400 million each, require only 7 to 8 tanker flights for HLS refueling, eliminate gateway requirements entirely, and provide superior safety margins throughout mission operations. Zubran's Dragon alternative needs just 2 Falcon Heavy launches total, offers immediate implementation using proven systems, provides reliable crew transport with operational history, and enables direct lunar orbit operations without intermediate stations. The cost differential isn't marginal, it's transformational. These alternatives represent the difference between a sustainable, long-term lunar program and a politically driven program that occasionally reaches space. Artemis 2 preparations continue despite these alternative proposals. The spacecraft completed fueling operations and advanced to final processing stages. 4 CubeSats will deploy during the mission, carrying experiments from various NASA partners. The crew, Reed Wiseman, Victor Glover, Christina Hammock-Cook, and Canadian astronaut Jeremy Hansen, will make the first human lunar mission in over 50 years. Their April 2026 launch target approaches, while Artemis 3's surface landing remains years away. NASA's Global Outreach Program invites international partners and private citizens to help track Orion during its mission. The initiative demonstrates sophisticated mission planning capabilities, but doesn't address the underlying architectural inefficiencies. Every Artemis delay strengthens the case for alternative approaches. Each cost overrun makes the engineering solutions more attractive to budget-conscious observers. The implications extend beyond American space policy. China's lunar program advances with focused efficiency, prioritizing engineering results over political considerations. Their approach mirrors what these American alternatives represent: direct paths to objectives without unnecessary complexity. Private companies like SpaceX continue demonstrating that rapid innovation can solve engineering challenges traditional aerospace considers intractable. The success of Falcon Heavy, Crew Dragon, and Starship development proves these alternative approaches aren't theoretical. They're achievable with existing technology and methods. The fundamental question becomes whether America will choose engineering excellence or political expediency for its return to the moon. The technical capability exists for either path, but the decision will shape not just lunar exploration, but America's leadership in space for the coming decades. Here's what makes this story even more compelling. While NASA clings to Artemis, SpaceX isn't waiting for permission. They're already testing Starship components that could enable these alternative missions. Every successful Starship flight proves the Stubby concept is achievable. Every Dragon mission demonstrates superior crew transport capability. The real kicker? Private lunar missions are accelerating. Companies like Intuitive Machines and Astrobotic are proving that commercial approaches work. When private entities start landing on the moon cheaper and faster than government programs, the political calculus changes rapidly. But here's the question that should keep NASA administrators awake at night. What happens when China lands astronauts on the moon using a streamlined approach, while America is still assembling gateway components? The optics alone could reshape global space leadership permanently. The evidence is clear. The alternatives exist. The technology is proven. The only question remaining is whether political courage will match engineering excellence. Based on what we've seen, that answer might come sooner than anyone expects. What do you think? Should NASA abandon Artemis for these superior alternatives, or is there something we're missing? Drop your thoughts in the comments because this debate is far from over. And if you want to stay ahead of the space race drama, hit that subscribe button. Future Space brings you the stories others won't tell. The next episode reveals how SpaceX's Mars plans could make the moon look like a practice round. You won't want to miss it. What if SpaceX just tested game-changing technology on Flight 10 that NASA doesn't even know exists? While everyone celebrated the successful landing, 3 mysterious metallic tiles were secretly conducting the most important experiment in Starship history. Not the standard ceramic ones, something completely different. The orange streak down Starship's side? That wasn't damage. That was proof of concept for technology NASA abandoned 50 years ago, believing it impossible. But SpaceX didn't stop there. They also tested their secret weapon, the crunch wrap, a revolutionary sealing method that could finally solve the reusable heat shield puzzle that stumped engineers for decades. Let's dive right in. Picture this: August 26th, SpaceX's most critical moment. After 3 consecutive failures, Flight 10 wasn't just another test. It was make or break time. NASA's Artemis 3 mission, humanity's return to the moon, hung in the balance. But while the world watched for explosions, SpaceX was conducting something far more revolutionary. Those 3 metallic tiles weren't random. They were the resurrection of technology NASA studied extensively in the 1970s but ultimately abandoned as too complex for the era. What NASA couldn't achieve with 1970s technology, SpaceX believed they could crack with modern engineering. The genius? While everyone focused on the 18,000 standard ceramic tiles, SpaceX was testing the foundation of truly reusable spacecraft. Not just reusable boosters. We've seen that. We're talking about something no human has ever achieved, a heat shield that survives orbital reentry, lands, and flies again without months of refurbishment. Here's what nobody's talking about. The Space Shuttle program cost $196 billion over 30 years, and every single orbiter required 9 months of heat shield repairs after each flight. 9 months, that's not reusability. That's rebuilding a spacecraft every mission. SpaceX's Bill Gerstenmaier, former NASA Associate Administrator, revealed the shocking truth at the Glenn Space Technology Symposium. Those metallic tiles oxidized extremely nice in the high oxygen environment, creating that distinctive orange streak. But here's the twist. This wasn't failure. This was data collection on an unprecedented scale. Think about it. SpaceX deliberately exposed these tiles to plasma temperatures exceeding 1,650 degrees Celsius, hypersonic speeds of Mach 25, and the most brutal environment imaginable. The orange oxidation? That's pure intelligence on how metals behave in conditions that would vaporize most materials instantly. But the metallic tiles were just the opening act. The real revolution was happening underneath. Literally, SpaceX engineers discovered that their biggest enemy wasn't the plasma itself, but the gaps between tiles. Even microscopic spaces allowed superheated gas to penetrate, burning away protective layers and creating those telltale white patches visible on Flight 10's hull. Traditional solutions? NASA used gap fillers, small ceramic pieces wedged between tiles. Sounds simple, right? Wrong. These fillers regularly failed, popped out during flight, and created dangerous turbulence that actually increased heating. The Space Shuttle Columbia disaster taught us how deadly